Okay, let's take a look at our homework from last night, which was worksheet number 12. We got 3 questions that we want to go over here, number 2, 4, and 5. Let's go number 2 first. All right, it says, how fast must an electron be traveling through a magnetic field of strength 3 times 10 to the negative 3 Tesla if it follows a circular path of radius 6.5 times 10 to the minus 2 meters? As part of checking our homework, we'll do a little bit of review as well. We learned yesterday for the first time that charged particles, when they go through a magnetic field, experience a very specific path, or they travel in a very specific path. Prior to that, we learned that there's a force, right? Charged particle generates a magnetic field. A moving charged particle makes its own magnetic field. If there is an external magnetic field caused by magnets or the earth or whatever, then the two magnetic fields will interact and there will be a force. We learned that that force is equal to QVB if what? If what condition is met? That force is equal to QVB. They got to be perpendicular to each other. If they're not perpendicular to each other, then you got two options. They're either parallel to each other, in which case the force is 0, or they're in between perpendicular and parallel, in which case the force is something else that we don't have to be able to calculate in physics 30. So if they're perpendicular, this is what the force will be. Now, that gives us only the magnitude. We can find the direction by a hand rule that we used, in fact, on today's quiz, the hand rule for deflection. It says, thumb in the direction of the particle, stretch your fingers out this time. Don't bend them, stretch them out straight. Put those fingers in the direction of the external field. So in this case, it would be downwards from north to south. Thumb to the right, fingers downwards, palm would point out of the page in this case. That would be the direction of the force. Now, that's what we learned a few days ago. Yesterday, as I said just a second ago, we learned specifically the shape of the path of this particle as it goes through the magnetic field will be circular. Now, because it goes in a circle, there's another equation that we can use in addition to this one, and that is the centripetal force equation. What is that equation? I'm going to ask you what that equation is because it doesn't actually appear on our data sheet. We have to either derive it from a couple other equations on our data sheet, or we have to remember. Lewis, what is it? Good. It's m times v squared over r. Centripetal force. Now, because a centripetal force, you learned this in physics 20, a centripetal force is not a fundamental force. It's always caused by something else. A car going around a turn experiences a centripetal force. Well, it's caused by friction. The Earth going around the sun experiences a centripetal force. Well, it's caused by gravity. The electron going around the nucleus experiences a centripetal force. Well, it's caused by the electric force. Centripetal force is always caused by something else. Because it's always caused by something else, it's always equal to something else. In this case, the centripetal force will always be equal to the magnetic force. So we can, if we want, use either of the equations that I have squared off up here, or I can use a third version of it, and that is the combination of these two forces, Fc is equal to Fm. All right, now question number 2 is asking us how fast an electron must be traveling through a magnetic field if it follows a circular path of that radius. I'm going to circle electron in red, and we want to highlight things in a ugly colored highlighter or a red pen or something to draw attention to the fact that it's an electron, so that if I need to use a hand rule, if I do need to use a hand rule, then I remember that it's going to be a negative particle in a left-hand rule. It's going through a magnetic field. It's talking about the circular nature of it. It mentions the word radius, the circle of radius, 6.5 times 10 to the minus 2. Which of those 3 equations do you think you want to start with? Remember, they're all valid. Okay, for all of these questions, all of those equations are valid. And they will be every single time a charged particle moves perpendicular through a field. But which one do you want to try first here? Good. That's the one I'd try first as well. Fc is equal to Fm. I told you guys yesterday that generally, if you see the word radius in the question, in the context of a charged particle in a magnetic field, that is, if you see the word radius in the question, then you're going to try Fc is equal to Fm. Doesn't mean it's going to work, okay, but at least it's worthy of trying. Now, if you have an insight, it's a question that maybe you look at it and say, oh, wait, I'm just going to use this one because you have an insight, then go with it. Because even if your insight was wrong, it just means that you have to try another equation, right? It's not a big deal. Okay, when we try this one first, Rucker pointed this one out. We try this one. That one might not work for us either. It's not a big deal if it doesn't, because it's a valid equation. It's not going to give us the wrong answer. Okay. If it doesn't work for us, then we try another one. That's all. Fc is equal to Fm. That means mv squared over r is equal to qvb. One of the v's cancels. It leaves us with mv over r is equal to q times b. Now we're looking for v here. So let's rearrange this to solve for v. The r goes up by multiplying, and then the m goes down by dividing. So q times b times r, and now the m goes down by dividing. It becomes over m. QBr over m. So it's an electron. We know the charge. 3 times 10 to the minus 3 Tesla is our magnetic field. R is 6.5 times 10 to the minus 2 meters. And we divide that by the mass of the electron, 9.11 times 10 to the minus 31. Now, I don't remember what that works out to be, but I think we can all calculate that at this point. Turns out, if we had have not circled electron in red, we would have been okay here, right? Because we didn't need to use a hand rule. We weren't looking for a direction. Okay, that's just something that I do when as soon as I spot something like that, an electron, just in case. If it doesn't help me, then look, I just wasted a tiny little bit of ink. It's not the end of the world. If it does help me, then great. Is that okay? What was the issue? Was it rearranging or? Okay, you're good there now. All right, number 4. What's the kinetic energy in joules and electron volts of an alpha particle that moves through a magnetic field, follows a circular path of that radius? You know what? It's probably not a bad idea to do this. Look at what I did when I showed you the answer key. I forgot to convert to electron volts. And why did I forget to convert to electron volts? Well, because I knew what I was solving for. I knew I was solving for energy. I got it in joules. I just stopped. I was careless. Right? I was just being careless. If we draw attention to things like this that may lead to a careless mistake, then we're a lot less likely to make that careless mistake. I didn't do that. Okay, and I made a careless mistake as a result of that. So we want the energy in joules and in electron volts here. Now here's the thing. This charged particle is going in a circular path. Okay, odds are we're going to try the same equation we tried the last time. Fc is equal to Fm. Now I know some of you, when you were working on this, are thinking, well, wait, we're looking for kinetic energy. We're not looking for anything that we've solved for so far. We're looking for something different. That's okay. Don't worry about that. You always should do what you know is good. It doesn't matter what you're looking for. You know that a charged particle moving through a magnetic field experiences a magnetic force, experiences a centripetal force. We know those forces are equal. So even if we don't know how that's going to get us the answer, that's okay. Just try it. See what happens. What do we end up getting out of this? Well, we end up solving for speed. mv squared over r is equal to qvb. These cancel. We're left with v is equal to qbr. Oops. QBR over m. That gives us the speed, right? It's an alpha particle. I should have circled that. It's 3.2 times 10 to the minus 19 for the charge, times 0.10 for the magnetic field, times 0.025 for the radius. And the mass is 6.65 times 10 to the minus 27 kilograms. Now, I don't know what that works out to be for the speed. I'm guessing something times 10 to the 5-ish meters per second. Let's go with the unrounded number, though, actually. 1 point. Times 10 to the 5. Okay, good. All right, there's the speed. Okay, that's not what we're looking for, but that's okay. We solve for it because we could. I've told you guys this before, and I'll say it again. Sometimes, it's not often now that I see a new question, a unique question that I've never seen before, but it happens. I still sometimes see a question that I've never seen before, especially, when diploma exams come around, especially when they release questions. I see questions that I've never seen before. Now, if I write the diploma exam and I see all these new questions. Am I going to get 100%? Well, unless I make silly mistakes, careless mistakes, which happens, right, for me as it does for you, then yeah, I'll get 100%. And I can confidently say that. And I can confidently say that not because I'm smart, although I think I am smart, but so are you. You're just as smart as I am. Okay, I might know more than you do, but you're just as smart as I am. Okay, I think we're all smart people here. That's not why I'm confident we're going to get 100% on the diploma exam if I'm not making careless mistakes. I'm confident that I'm going to get 100% on the diploma exam because I'm confident. I'm confident in solving problems. And that's what you need to be as well. Look, I see a question like this. Look, I know how to do this question right off the top because I've seen it a bunch of times. But even if I hadn't seen it a bunch of times, I'm looking for kinetic energy. Maybe I've never done that before. It's okay. Look, I did something that I know, and I wasn't afraid. I just tried something, and I got speed. Hey, look, it's not what I'm looking for. But usually when you do something that is valid, it's going to lead to something. And that's what's going to happen here, right? We just solve for speed. Hey, we got speed, we want kinetic energy. Now it's easy. EK is equal to 1/2 mv squared. You don't have to be brilliant to do this. You just have to not be afraid to try, not be afraid to make a mistake, not be afraid to fail this question. All right, so we got 1/2 of the mass, 6.65 times 10 to the minus 27 kilograms, times the speed squared. What do we get there for the kinetic energy? Yep. Oh, is the speed wrong? Okay, so what do we get? Times 10 to the 5. Okay, thank you. So let's fix it right there. And what do we get for the kinetic energy there? I assume it's what I had on my answer sheet there, Jack. Okay, so there's my answer. There's my answer in joules. Yep. There's my answer in joules. But we got to convert it to electron volts. We've done that a few times. Okay. Odds are there's a pretty decent chance you'll have to do that at some point on your diploma exam and probably on another couple of unit tests leading up to that diploma exam. So let's go through that again now. On our data sheet, it says 1 electron volt is equal to 1.6 times 10 to the minus 19. Now, it doesn't express as a fraction like I have. It just says 1 electron volt equals that. Okay, I'm expressing it as a ratio. If 1 electron volt is 1.6 times 10 to the minus 19 joules, then X electron volts is 4.8 times 10 to the minus 17 joules. Okay? This to this is the same as this to this. So we solve for X here. The 4.8 goes up by multiplying, and then we divide 4.8 by 1.6. It gives me 3.0 times 10 to the 2 electron volts. And there we go. Is that good? How many people got that question? Good. Good. Once again, guys, it's amazing how, you see a question like this that looks a bit challenging because, hey, we've never solved for kinetic energy in this context before. Looks a little bit challenging. If you are not afraid to try, then it's amazing how often you actually get it. Not always. Sometimes we're still going to miss the question. But it's amazing how often we end up being successful. If you're afraid to fail, you will fail. Okay? If you're afraid to get a question wrong, you will get a question wrong. Don't be afraid to try things. Okay, number 5. 5 says, how does the radius of curvature of an electron compare to the radius of curvature of an alpha particle? It really should say of the electron's path and the alpha particle's path, because we're not talking about the radius of the electron and the radius of the alpha particle. We're talking about the electron's path and the alpha particle's path, right? Same magnetic field, same speed. Let me ask you a question here. let me preface the question actually though with something. Let's pretend you're 20 years old. You're not. None of you are 20 years old. If you are, you look very young for your age. Okay, but let's pretend you're 20 years old. Okay, Janessa, you're 20 years old now. You're grown up. You can vote in the next election. You're 20 years old. Let's pretend I'm 40. I'm not 40, but let's pretend I'm 40. All right, so how do we solve this question? After that brief digression there. We're pretending you're 20. We're pretending I'm 40. If we wanted to compare my age to your age, how do we do that? What's the comparison of my age to your age? You could subtract. Yeah, you could subtract. You could say that, oh, Mr. Dickie is 20 years older than me. Okay, so he's 20 years older. That's a comparison. That's a valid comparison. But it's not the best comparison. And I'll tell you why. 20 years can mean not literally two different things, but it can mean two different things, depending upon the ages involved, right? You're 20, I'm 40. That's quite a difference in age. You're 1 and I'm 21. That's a much bigger difference in age. You're 90 and I'm 110. Oh, we're all just old in the same home, right? So it's not that much of a difference in age then, right? So you can compare by subtracting, but it's not the best way of comparing. What's the best way of comparing? Let's divide. Yeah, let's divide. Let's find a ratio. Right now, I would be twice your age, right? If I'm 40 and you're 20, I would be twice your age. Let's do that here. Okay, we want to divide these two radiuses in order to compare them the best way. Put it away, Rucker. We want to compare the radius of path of the alpha particle to the radius of the path of the electron. Sorry, the electron to the alpha particle. Let's create a new page here. The radius of the electron's path to the radius of the alpha particle's path. So let's divide RE by R alpha. Just like if we were comparing my age to your age, we would divide my age by your age. If you're comparing your age to my age, we divide your age by my age, right? So whatever we're comparing from goes on the top, to goes on the bottom. Now, when we divided my age by your age, we already knew the ages, so it was an easy question, right? 40 divided by 20 is equal to 2. We don't know the radius of the electron's path and the radius of the alpha particle's path. Hey, let's find it. Let's find it. Let's say FC is equal to FM. Let's say mv squared over r is equal to qvb. Let's cancel out these, and let's solve for r. Okay, the r goes up by multiplying, the qb goes down by dividing. R is equal to mv over qb. Hey, we know the mass of the alpha particle and the electron. We know the charge of the alpha particle and the electron. Hey, but we don't know the speed, and we don't know the magnetic field strength. So we can't even find r. How do we divide two r's when we don't know what the value of either one of the r's is? Well, let's put in an expression here. John? Yep. Yes, yes. And I'm going to show you mathematically why that works here. The radius of the electron's path is ME VE over QE times BE, right? All the information about the electron there, right? Let's do the same thing for the alpha particle now. Okay, it's M alpha V alpha over Q alpha times B alpha. Here's the good news, and this is what John was alluding to. The speed is the same. The speed of the alpha particle and the speed of the electron is the same, so it ends up canceling out. The magnetic field, they told us in the question, is the same, so it ends up canceling out as well. Got one on the top, one on the bottom. That leaves us with four numbers that we know here. The mass of the electron, the charge of the electron, the mass of the alpha, the charge of the alpha particle. Let's calculate this ratio now. Now this looks a little bit confusing with all these divisions here. What I would suggest you do is get a number for the top, calculate that. Get a number for the bottom, calculate that. Get two numbers and then divide the two. Let's say this side of the room here, okay, this side of the room and over is going to get the number on the top. This side of the room over here is going to get the number on the bottom, please. 5.69 times 10 to the minus 12. And the bottom number here. Hayden, you got that? Agree with that, guys? Yep. All right. What's the quotient there now? Sorry, I got a little typo here. This should be 10 to the minus 8. What's the quotient there now, Riker? It's 10 to the minus 4. Okay, thank you. Okay, so what does that number mean? Well, if the ratio of my age to your age is 2 to 1, because we divided 40 by 20 and got 2, then the ratio of the electron's path to the alpha particle's path would be 2.74 times 10 to the minus 4 to 1. So if we want to express it as a ratio, then that's the easiest thing to do. All right? Make sense? Listen very carefully to the next sentence I'm about to say. In physics 30, whenever you want to compare two things, divide. Done. In physics 30, whenever you want to compare two things, divide them. Now, if you're lucky, you may have the numbers, and all you have to do is divide the numbers, like 40 divided by 20 is 2. If you're not lucky, then you may have to calculate the numbers and then divide them. If you're even less lucky, I should say, you may have to actually put the expressions into the equation, the division equation, so that you can cancel some things out. But the bottom line is, whenever you want to compare two things, divide. Same goes if you're asked to find a ratio between two things. Divide. Ratio, compare, all of the above means divide. Got it? All right. Have a look at the diagram you see up on the board right now. This is a diagram of something called a cyclotron. A cyclotron is one kind of particle accelerator. Charged particles that are subatomic, we sometimes accelerate them to incredibly high speeds. There's a particle accelerator that straddles the border between Switzerland and France called the Large Hadron Collider. You've probably heard of it on the news. They just fired it up actually just a couple of weeks ago. It's been undergoing repairs for quite a long time. It's the world's most complicated, the world's biggest machine, and because of that, things break down, right? Things break down, and it breaks down often. So they just got it up and running here a couple of weeks ago again. A couple of years ago, using this Large Hadron Collider, they first observed for the first time this particle that some people call the God particle. It's this special particle that's responsible for mass. It had been theorized for decades, but nobody had actually ever observed it. We observed it a couple of years ago. So now we know that it actually exists. This particle that's responsible for mass, that results in us and everything else having mass. We accelerate subatomic particles to incredibly high speeds, and then we smash them into each other. It's like we want to find out what's inside. You got to break them apart. Now, when you break them apart, these particles don't want to break apart. So you got to get them going really fast. You got to get a lot of energy into these things to break them apart. It's kind of like, you know what? You're in a parking lot, a Walmart. You're driving in a parking lot and at 4 kilometers per hour, and you hit another car at 4 kilometers per hour. Maybe you put a scratch in the bumper. Maybe you put a little dent in the bumper. But you're not going to find out what's inside the car by colliding at 4 kilometers per hour, right? If you're traveling on the highway opposite to one another at 115 kilometers per hour and you hit, then the cars are going to virtually disintegrate. And you're going to find out what's inside the car because pieces are going to fly everywhere, right? If you want things to break apart when they crash into each other, they've got to be going incredibly fast. And that's what we do with these cyclotrons. We get them going, these particles going incredibly fast, such a high energy, so that when they smash into each other, we can break them apart, like those two cars going at 115 kilometers per hour. Now, there's two things involved here. First of all, how do we get them going so fast? Okay? And second of all, how do we guide them? How do we control where they're going? Well, how do we get them going so fast? We actually use an electric field for that. I know that's kind of last unit as opposed to this unit, but that's okay. An electric field between these Ds. And if you're wondering what that word means, Ds, it means literally Ds. There's two Ds. We've got one right here, and we've got one right here. And then we've got this gap in between, you can see. This gap in between has an electric field. And when these charged particles go through that electric field, what happens to them? Speed up, right? They speed up. So a charged particle goes across, starts right here. Okay, this is the ion source, starts right here. Okay, goes in a circle. We'll deal with why it goes in a circle in just a moment. It speeds up. And then it keeps going in a circle, and then it speeds up. And then it speeds up. And then it speeds up. Every time it goes across a gap, it speeds up more. That's how we get it going faster and faster and faster. But in order to get it going across that gap multiple times to speed up, speed up, speed up, speed up, as opposed to just once or twice, we've got to control where it goes. We've got to control the path that it takes. Now, we want it to go in a circle, hence the term cyclotron. Okay, go in a circle. That way we can go across the same electric field time after time after time after time, and we can minimize the area of the cyclotron. So it goes across an electric field, another one, another one, another one, another one, another one, and so on until it's going 99.99% the speed of light. Smash into another one, disintegrates, see what's inside it. Okay. How do we get it going in a circle here? We introduce a magnetic field. Right? The magnetic field causes it to go in a circle here. The question that I have for you right now is, what direction does that magnetic field have to be pointing in order to cause these particles to go in the circle that they're going? Hey, did you notice something actually? It's not quite a circle, is it? It's more of a spiral, right? Why is it a spiral as opposed to a circle? Didn't we say that a charged particle going through a magnetic field always goes in a circle? No, not quite. We said a charged particle going through a magnetic field always goes in a circle if it's perpendicular to the field and if it stays the same speed. It's speeding up here, right? So the radius of the circle is going to keep getting bigger because it speeds up, right? How are we going to figure out? How are we going to figure out now what direction the magnetic field has to be to cause it to go in this, we're going to say circle, even though it's not quite a circle. Yep. Yes, we do. We need to know whether we have positive or negative ions first. Good. Let's assume that they're positive. So we're colliding protons together. Positive ions. Okay, that's step one. You're absolutely right. What's next? Well, if these charged particles are being deflected by an external magnetic field, we're going to use a hand rule. And it's going to be the wire-grasp rule, the coil rule, or the hand rule for deflection. Who says the wire-grasp rule? Who says the coil rule? Who says the hand rule for deflection? Okay, most people are right here, the hand rule for deflection. The reason is, guys, these charged particles experience a force. It's a centripetal force pointing toward the center of the circle. I'm going to say, I want to use my right hand here, stick my thumb in the direction of the particle. Right, Zane? Stick my thumb in the direction of the particle. The problem is it's traveling in different directions all the time, right? It's going up, over. How do I know which way to stick my thumb? Don't get confused here, guys. This is not a coil rule or a wire grasp rule because, oh, look, my fingers point nicely in a circle here. We're not doing that. My thumb has to point in the direction of the particle here. But the particle's always changing directions. Yep. Yeah, it is. Okay. But we have to pick a specific spot. So if you want to do it at the ion source, that's fine. I would actually rather do it towards the outer part of the circle. Okay, whether you do it here or here or here or here, it doesn't really matter. You know what? I want to pick a spot here because there's not a lot of writing there. I got space to draw. At this point, the charged particle is going this way. Now, at this point, it's going this way. At this point, it's going this way. Let's look at position 1. At position 1, I can stick my thumb in the direction of the particle, which is toward the top of the page. My fingers go in the direction of the magnetic field. I don't know which way that is, but I know my palm goes in the direction of the force, which is toward the center of the circle. So if my palm goes toward the center, which way do my fingers automatically point? Into the page. So my magnetic field here would be into the page. Now let's assume you picked this point up here as opposed to this point over here. Thumb in the direction of the particle, which is to the left. Palm points downward toward the center of the circle. My fingers point into the page. So it doesn't matter where you do it. Rucker, your way would have worked just fine. Yeah, I just thought it looked a little less cluttered over on that side, that's all. You're going to get the same answer any way you look at it. Make sense? All right.